Hi guys, Cyprien here, and in this video we'll talk about the graph comment. So this video is the next video in the series OnScale Analyst 101, and I will teach you how to plot your model using script in OnScale Analyst mode. So let's start. So I will show you the basic of how to use this command, the graph command. So I call it graph, but if you look at it very well, it's grph because the number of characters is limited to 4. So sometimes, you just write the script and you forget about that and you just write graph with an A in between and it doesn't work. So the first thing to be careful about is that do not put the A, it's grph. And I'll show you this model. So this model is a 3D transducer here, and the part in violet is water around it, and this is a half transducer. So I'm showing how to create and build this model step by step in another video within the designer mode of OnScale because I have imported this model from CAD. And now in this video, I'll show you the script part of it. So I basically generated with Designer, and now I'm looking at the announced script. So the basic function to plot the model is graph plot match, where match means material. So, and this will plot like that in the runtime graphics, the materials which are defined in your model. So, and you can preview this model in the script using the preview function, which is here in the main toolbar. So if you click on preview, what the OnScale will do is that basically it will run the model until it meets the first graph comment in your script, and then it will render it into this window. But what is interesting to note also is that this command, once you launch it, it will pause on the term command. And then this console command will become activated, allowing you to basically enter some new option on the run. So while the command is writing, so you don't have to preview, stop, change the code, preview, stop, change the code. You can preview, go there, input your options, and replot like that without having to relaunch everything every time. And this is important because for this model, for example, every time it's run using the preview, it has basically to remesh everything. So, if you have a big model which needs some time to be meshed, well, I don't want to, to remesh it every time. So let me switch to OnScale and show you all of that. So this is the announced code which corresponds to this model. Again, if you need this model, I'll put it as a download in the description, and I will also put the link to the tutorial video showing how to make this model using designer mode. So now I'm basically going down into the code until, so here I'm at the material sections. Here, this is the site section where the materials are assigned, the boundary conditions, the calculation of the output, the Piezo loading of the electrode. And basically, the first time the graph function is in my script appears here. And this is what basically the preview function will plot. So you could place it here, or you could place it before as well, because you can place it right after the site and before the boundary condition. So that's probably the best place to put it. So I'll just cut that and put it here just after site, like that. Okay, now let's run the preview and see what I get. So now it will plot all the materials which are inside my model. As you see, it takes a bit of time because the model needs to be meshed, and I obtain the model in the runtime graphic window here. So like I told you, I can now enter directly some options here in this window. So for example, So the first thing you need to do here in this window is to input the name of the command you want to input. So grph, like graph, enter, and I am now about to enter the sub commands like that. So if I enter, I don't know, plot, and I want matte material, it will basically replot this. So now I only show you one command, which is how to plot the material. So it's not very interesting. So let me switch back to the tutorial and show you more what kind of option you have using this runtime graphic window. So, and I'll stop the preview for now. Now let's talk about standard graphics. So what you should know is that before using the current visualization like this, called the runtime interactive graphics, where you can rotate and zoom your interactively on your model, OnScale had what is called the standard graphics. So it was a bit more rigid because you have no way to rotate the model inside this window, and basically this is just a picture. But the advantage of this standard graphics is that some options which are not available in the newest one are available, like visualization of the finite elements with the line on option. So let me show you what you get by doing this. So again, I'm going to the graph command, and now I type standard and line on. And so the type standard command will switch to the standard graphics, and the line on will display the mesh element. So if you don't switch to standard graphics, this option doesn't work. So let's again run the preview. Okay, and now you see that I am displaying the full model with the mesh. Now we don't really see very well what this model actually is, because there is a big block of water, and the real interesting model is within the water. So what if I wanted to plot only the model inside this and make a zoom on that, for example? So let me get back to the slides. Or okay, so let me show you first how to plot one slice of the model. So it's possible to plot a slice of the model by adding some option after the matte. So if, for example, I do plot matte J60, it will find the slice which has the index 60, and it will just plot this slice. Let's try that. Okay. And now you see that I have, because I'm still running the preview, so I have this activated. So what I'll do is that I will use this. So graph, enter, and now I can plot J60. Oh, sorry, it's not, it's plot matte, forgot, J60. Yep, so it's executed, so now I have to view again, and you see if I look at the visualization window, it basically replotted the model to show me this slice here. Now, if I want to view only one part, there is a useful command called comb, which will basically combine materials. So the trick here is to combine a material with void to make it transparent, so basically remove it from the visualization. So if I do comb matte void water, it will basically combine the water and the void material, so the water will disappear. And then I have to plot again the material. So let's try. So again, I still have activated this view. So now I will replot the total material matte like that. So if I look at the window, I have again this, right? And oh, you know what I could do? You can actually like that, put this, because yeah, let's put it like that, and let's take out the console. So it would be a bit more interesting because I will be able to let's make that a bit smaller. So when you make it small like that, it doesn't rescale automatically. So what you have to do is basically to plot mat again, like this. So now you see I have visualization of my window and the console, so it's a bit more practical. If you have two screens, it's even better. Now let me show you how to show only the inner material. So let's use comb mat and combine the void material with the water material. Okay, so you see nothing happen. That's because now I have to replot again the material. And now the magic is here. So it basically it has hidden the water, and it left only the other parts of your model that you can visualize. Okay, now let's talk about something interesting for people working with Piezo, because OnScale, one of the big applications is Piezo type of simulation. So this model is a transducer. This part here in green is a piezo disc, and there are two electrodes on both sides. And how can I visualize those electrodes within my using those functions? So there is a function called Piezo. So by default, if you have some electrodes which are defined within your model, and you plot Piezo, you're basically displaying the nodes of the electrodes. So this is useful because sometimes you're not very sure where your electrodes are defined or if they are correctly defined. So you can use this function to view what is the real electrodes that you have defined. Let's have a look. Okay. So let's stop the preview, and let's start from this preview function. So I had plot material, so instead of doing that, I'll just replace that by Piezo, like Piezo. And if I preview again right now, yes, I know. Yeah, that's because the piezo electrodes are defined after my graph function. So, okay, that's basic mistake. So it's good that I'm doing this mistake, because you saw that before at the beginning of this video, I changed this code and I placed it before, just right after the site command. So now the electrodes have not been defined on this model, and I'm trying to visualize them, which is, of course, a bit silly. So let's just cut that. Let's go down and let's put this visualization right after the prcs command. So this command prcs check the model integrity right before the execution of the calculation. So it's also a good place to place a graph. Let's put it here and let's try again. Okay, it's good. Now it finally show me the two electrodes that I have defined within my model. So let's see if there are other options which are interesting. So what you can do also is plot the polling directions. So using the function arrow poll, because you know that the electrodes are polarized in one direction, so it's useful to see that. Well, especially if it's not a direction which is perpendicular. So maybe you have a sphere, or you have a cylinder type of polarization. In this case, it would be very useful. But anyway, let's try that. So let's make that smaller again. And let's plot. Okay. Okay, so now what I have to do is arrow pull and plot Piezo again. And now you see that I'm able to plot the polarization of those electrodes, which is nice. Now what you can do also is to plot together the material and the electrodes and the polarization. So if I do again, let's just stop the preview. Let's change the code here. Sometimes it's better to do like that. Standard light on. So if I want to hide my water, so I have to do comp mat void water, right, like that. Now I want to plot the material and the piezo electrodes. So I plot mat and piece like that. And I forgot to add the arrow pull to plot the polarization. And now if I preview the model again, yep, so now you see that I'm visualizing my model, and here I visualize the two electrodes on both sides of my piezo material and the polarization of those electrodes. What can I do more than that? So for some models which are maybe have unusual shapes, it can be difficult to see different section, different shape of the model, because this standard view is kind of rigid. So if you use just plot mat, you'll get this view. You don't know what is between those two. So of course you can say, well, why not come back to the runtime graphics? Well, suppose that I still want to see the mesh, or I want to have some nice screen capture, or I don't know. So there are some ways basically to change the orientation of this, either for 2D or 3D model. So note that you have the small coordinate system here, which is displayed, which show you where is the X, where is Z, and where is Y axis. So let me show you how to change the view. So the way views are defined in OnScale, so there are several ways to basically recenter or change the view. And the one which is usually used is called I. So you have to think about as if you had some eyes somewhere. Just imagine the small coordinate system like that, Y, X, Z, and you have your model oriented like this. And just imagine that you are moving into this coordinate system, and your angle of view is basically always with the model at the center. So if you go here, what will be your coordinates? You will be, let's say, on the 0 y-axis, on the 0 z-axis, but you will be on the 1 x-axis. So the command that you have to write is I100, because you are now on the x-axis, and the view that you will get is this one. So you will see the model from this angle, and you'll see this face basically. Now, if you think that you go instead of the y, you travel to the y-axis, and let's say you move just a little on the x and z axis, just to get a bit more perspective, and this is what you get. So you get a view from the back like this. Now, if you go, let's say, at 1, 1, 1 in each of those directions, you move one in X, one in Y, and one in Z direction, then you'll basically view the model from this symmetric angle, so which is this view, etc. Well, let me show you in OnScale how to use this, how to change the angle. Okay, so I just opened a new model just to show you the demo. And for the moment, I have graph plot match, so the most basic type of visualization. So preview model, this is what I get. So this is the runtime interactive graphics. You see the model shape is like that. So basically, if my view is like this, I don't see this part here. Now, let's switch to type standard. So type standard and line on like this. And let's preview the model again. Now you see that the basic angle which is given is this one. So, well, I can see the whole model, but let's say that I'm interested to change the point of view. So if you remember, if I place myself in the x-axis here, using the I function, I should be able to see the model from this side. Let's try that. Let's stop preview. And to use the I, just go before that, type I. So 1, 0, 0 to place myself in this direction. And it works. So now I am able to change the view. And you see that the orientation of the coordinate system here shows where you are. If now I want to go from, let's say, I want to visualize from the rear of the model, I'm looking at the y-axis, just preview that, and I'm sit from this. So it looks like a plate, so a 2D plate. So that's why maybe sometimes if you want to make some screen captures, it's better to add 0.01 to add a very small offset. That like that, it looks a bit 3D. It doesn't look like a plate. Now, let's go back to the slide. What is interesting also is that you can see several views at the same time. And there is an option called N view, but be careful, there is no I. It's only NVEW, NView, but without the I, because it's limited to 4 characters. So if I use, let's say, here, I use this N view, and let's say 2.1. Now I'll tell you after what those numbers mean. And now I'm interested to plot 2 types of visualization. So the first visualization will be the one with I 1, 0, 0, plot match. And then I'll change the camera and I'll plot in the second window. So it's basically sequential. Now this command tells that I want 2 views, and the first view will be using the I 1, 0, 0 for the orientation of the eye, and the second view will be using this. So let's see what I get. If I preview, now I get 2 views like that. The first one will be the first definition, and the second will be the second one. Now, if instead of 2.1 I define 1.2, you can guess what I will get. Okay, I get nothing. Okay, so how do I know what those numbers mean? That's the next question, right? Well, go into the help like that, and if you go to the help of this function, you see that it's written here. So basically the horizontal view is not 1, 2 like I hoped it would be. It's 2, 1. So it's very small, probably difficult to read, but I'll do a zoom like that. Okay, so now you see you have different ways to do. So let's just try that. 2, 2. Okay, and now I get the two views like that horizontally. So what if I want to plot four views? So 4 views will be 4, 1. And let's say in the, let's say like that, just copy paste, and I'll change the direction. So 1, 1, 1, and let's say 1, 2, -3. Why not? And now I get the visualization with the 4 views together. So those are the different viewing window arrangements that you can use. And if you want to plot data that you calculated, plot results basically, you have to understand also the structure of the code and where you should place your visualization graph command within the code. And for that, just consider the whole script as if it was divided into 3 parts. You have the first part, which is the model building code. That's what I've been showing to you up to now. And here you didn't start the calculation yet, so you can only visualize the models, the materials, and the loads, probably, all that. Now you have the execution loop. So this is the part where the model actually starts to be calculated. And you can view the result while you are calculating. So this is called runtime graphics. And so if you put your graph command within the execution loop, you'll see your results changing and be replotted while the simulation runs. Now, if you want to see, let's say, after the execution loop, while it has been calculated, well, you have to place it into the code which is after this execution loop. So let's have a look at how it works in OnScale. So I'm back with the code of the 3D transducer that I was showing you before. And let me find where is the execution loop, where is the model building phase. So basically look at the different comments because the comments come in the same order every time. Here I'm defining the material here. Now I have the side command which assigns the material to the grid. The bound command is the boundary condition for all the sides of my model. The car command is the definition of what I want to calculate. So it basically tells the solver, okay, I want to calculate the acoustic pressure. So I'm defining here press acoustic. I want to calculate the min-max acoustic pressure. So, okay, let's define like that. Others that you want to calculate are defined in calc. Piezo is the command to define the electrodes and the piezo loading. Time is to set up your analysis time. And the PRCS will check all of that. The graph here is what will display my model. And the pout is, so it's actually written here what those function does. So if you read that carefully, you can understand what this means. So this is to define the time history curves that will be displayed during the computation. So what is done here is that there are 3 variables x, y, z which are defined at a certain position in my model. Then I define then I put basically a probe at those 3 locations and I monitor the acoustic pressure x, y, z and I say that as a curve. And then the second curve in my history will be my input forcing function. And then there's a hist name electrode VQO. What this option does is that it will print voltage V and charge Q for all electrodes. So if you have 2 electrodes, it will first start with electrode 1, then it will register the voltage and the charge for electrode 1, then it will look at electrode 2 and register voltage and charge. If you want current, just add 1 here. And just go in the documentation if you want more details. So basically I'll have here 1, 2, 3, 4, 5, 6 time history curves that will be saved. Then if you look at this part here, as soon as you see the n exec, and it's basically written run the model, this is where the execution loop starts. And when you look at this function, you have to look for that. This is the actual execution loop. Well, it's called run plot procedure or whatever you want to call it, but it's remarkable because you have a proc something and you have an end with $1 here, proc. So what this does is that here I'm basically defining some kind of function so the name will be plot proc. The name of this function is plot and I save it. And within this function, I want it every step of the way to execute the following code. And right after this, I have a proc plot end loops, which basically will run this loop a certain number of end loop times. So if I place the graph here, like you see, there is a graph here right now. This graph is the one that will be plotted to the screen while I execute my model. So I'll show you that right away. And once this end loops are all over and finished, then in this last part here, I can plot the final results. So here I have no graph, but if I put a graph here, it will display the last results for the last time step. But I have some data command which basically put that to a file. So let's have a look at what this does. So what I expect here, if you see right before the loop, I have a graph nview22 set image TIFF. So it will basically set up the plotting. So I will have two views, which will be horizontal. It will set the image as TIFF. And this is to save an image file at every time I run a loop. Now, what I plot here is in the plot 1. Plot 1 means the first curve of the history. So which means if I go back to parts, this will mean this one. This is the first one that will be plotted in the left. And the second one will be plot APRS, acoustic pressure. So at the right, I will have acoustic pressure. You see, I have a mirror off, which means that I don't want to show the symmetry or to make the symmetry of this model. I just turn it off. I don't need this function here. I could just hide it. And there I have an image. This function will plot and save an image to my hard drive for every loop increment. So let's see. So I have run solvers. I'm using the local run. So you need, of course, to have a local license to do that, or a local core license, depending on what kind of license you have on OnScale. But this runtime graphics is also available on the cloud. So it's slightly different because you have to. There is a button, so you can also view it on the cloud. Anyway, now see my computer starts to because it's calculating now, so it's start to run. It's a bit noisy. Okay, and now you see that this is exactly what I was telling you. On the left, you have acoustic pressure recorded at a specific position that I precised, so which is exactly the exit of my transducer. So this is the acoustic pressure curve, which is plotted here. And here on the right, I have my acoustic pressure wave. So I have the visualization of the acoustic pressure result on the whole model. Now, if I wait until the last step and everything is computed, I'll basically have a term function a temp command here, and this will put all that in pause, like I did previously, and then I'll be able to play with the view and visualize the results interactively like this. Okay, so what else do I have for you? Okay, so this is basically what I was explaining before. The model building code. So this is the path. So you see that the path is to specify the different time histories I want to plot, like I told you. And then in the exec loop, I have two parts, the pre-exec loop and the part within the exec loop. So the part pre-exec loop is to set up the view, and the within is what is displayed while you compute the model. And this is to plot time histories, so that's also what I was saying. So just put it on some slides so you have better visualization of that. The path will basically, if this is defined like this, it's equivalent to that. The first will be acoustic pressure at XYZ. Second will be input function. And 3, 4, 5, 6 will be voltage electrode 1, charge electrode 1, voltage electrode 2, and charge electrode 2. So if I do plot 1, it will plot my first function. If I do plot 3, it will plot my third time history curve. Let's look now at the result once it's calculated. So you see that when the button here start to be activated again, and all the stage here that I define in my model are completed, the model basically is computed, and it is just in pause right now. So it becomes yellow, which means that I can start to play with the visualization post simulation. So now I have two views. Let's turn that back to one view. So first let's input the graph command again. N view without the I in 1, 1. And let's plot APRS. Okay, so now you see that I have only one view and I'm plotting only acoustic pressure. Now let's say that I want to see the acoustic pressure at a specific slice of my model. So like I did before, I can plot APRS, J, and I don't know, 150 maybe. So now I'm looking at only one slice of this. So of course, not that interesting. It's just to show you that you can, like that, dynamically change the view. So let's plot. Now let's plot the first time history curve. So the command is plot 1, and now I'm looking at the first time history curve, which is the acoustic pressure, APRS, at certain position. So the position basically is written here. You have the I, J, and K indices of the mesh element in which this position has been monitored. Now, if I plot 2 will plot me the forcing input function. So as you see, it is a recurve wavelet that I used. Plot 3 will visualize the voltage input at the first electrode, which is exactly like the forcing function because it is the forcing function. So it's the same, plot 2, plot 3. Plot 4 will visualize the charge. So this time it's a bit different because I'm visualizing the charge. And that's it. So if I wanted to visualize, let's say, several views, so N view 2, 2, for example, and I would do plot 1. So in the view on the left, I get the plot 1. And if I want to, let's say, plot, I don't know, the displacement in X that I calculated, I remember, I think. Let me look at the code. Because you cannot visualize arrays that you didn't calculate, of course. So you have to go back in the calc. Okay, I didn't calculate displacement. I have only the acoustic pressure. And if you go in the data manager main, okay, so that's a trick for you. If you go in the data manager window and you go into main, so you are able to view all the data arrays that have been calculated. So sometimes, you try to plot something and nothing, you just get 0 as a result. Maybe that's because you forgot to calculate it. So if you go back here, you can see that displacement is not calculated. I don't see x dsp here, but I have the velocity x vel, which is automatically calculated. So if I plot now the velocity x val, I'm now getting the velocity. And I'm looking at the last time increment because I have already calculated up to this point, and now my solver is in pause, waiting. And if I want to save that into a file, well, that's where the data commands come into play. So just basically data, file out, the name of the file, and out, and the result that you want to be written to a file, and then this will generate a file with the result inside it. Okay, so that's about it for this video. So I hope it was useful for you and that you learned how to play with the graph command at every level. There's, of course, always more to learn, but you have to dive into the documentation, look at what each command does in particular. But I hope that this video already gave you some good basics about how to start visualizing your plots or your datas. Thank you very much for watching.